Now we'll study the most fascinating of all operations on species, which is the operation of substitution. So as a motivating example, I'm going to consider the species of endofunctions. So NU is NU structure is just all functions f from u to u. And you can visualize an endofunction as follows. You can just think of it as a directed graph where every vertex has exactly one out edge. And well, transport of structure, I think I explained it earlier, but if you have sigma from u to v and s takes u to u prime, then so let's write it like this. If s takes u to u prime, then and u sigma takes sigma u to sigma u prime. That's the transport of structure. And visually it has this kind of a picture where you have a directed graph where every vertex has exactly one out edge, namely that edge tells you where the function f maps your element of u. And if you have an endofunction, there are two kinds of vertices in it. There are recurrent vertices. Maybe I'll call them recurrent points. These are the points u in u such that, so let's fix f. And so with respect to x, points u such that f to the power k u comes back to you for some k greater than 0. So for example, if you take this point here, this is a recurrent point because if you apply f once, you end up here, and if you apply f again, you end up here, and if you apply f 3 times, you end up at the original point that you started with. This point here, on the other hand, is not recurrent because once you leave this point, there's no way of coming back, nor is this. So in this connected component, only these 3 red points are recurrent. Let me just mark all the recurrent points in this endofunction. So this endofunction has these red points which are recurrent points, and the remaining points are called non-recurrent points. Now there's another way of viewing this endofunctions, and let me just change your perspective a little bit on this, and that is you can view each of these recurrent points. Let me draw them again. As the root of a tree. Let me draw the trees. So this recurrent point here is the root of, maybe I'll use black. This recurrent point here is the root of this tree. This recurrent point here is the root of this tree with only one node. This recurrent point here is the root of this tree. Similarly, this recurrent point here is the root of this tree. This recurrent point is the root of this tree. Here's another tree with just one node. Here's a tree with 3 nodes. So you can think of each recurrent point as the root of a rooted tree. And now what you can think of, these cycles, in fact, you can think of them as cycles between the trees themselves. So you can think of this cycle as actually a cycle taking this tree to this tree, this tree to this tree, and this tree to this tree. Oops. How do I erase this? There you go. This cycle takes this tree to this tree, this tree to this tree. So what we are saying is that we can regard an endofunction as, so now this is just a union of cycles, it's nothing but a permutation. We have here 1, 2, 3, 4, 5, 6, 7, 8, 9 trees, and we are just permuting them. So we can think of this as a permutation of trees. So I'll explain precisely what this means in general. Remember, A is the species of rooted tree structures. So an endofunction is just a permutation of rooted trees. It's clear how to go back from this picture here to this picture up here. You just have to take these green arrows and move them down to the roots, and you can recover the endofunction. So an endofunction is nothing but a permutation of rooted trees. So the notion of substitution of species is going to make this intuitive idea more precise. So here's the definition. Suppose F and G are species of structures and you need to make one assumption that G of the empty set is empty. So this is certainly the case for rooted trees, because you need at least one node to have a rooted tree structure so that you can have a root. Then the species F circle G, which is called the substitution of G into F. It is defined as F circle G. I'll write it down, it's a bit complicated, and then I'll explain to you exactly what it means. Sum over pi in partitions of U, F pi cross product over P in pi, which means that P is a block of the partition pi, G applied to the block. In other words, a F circle G structure on U consists of a triple, pi, which is a partition of U, phi, which is an F structure on the blocks of pi, and gamma, where gamma is a bunch of G structures on the blocks. So where pi is a partition of U, phi is an F structure on the set of blocks of pi. and gamma is gamma p, p in pi, where these are the blocks. Gamma p is a G structure on P. Let me give you a visualization of this and then we look at examples. Of course, we already looked at one example, so we'll go back and look at that first. So a general visualization could be that, okay, you have a set with a whole bunch of points and you want to put an F circle G structure on it. So what you do is you divide the set into blocks. So here's one block, here's another block, here's another block maybe, and on each block you put a G structure. And on the set of blocks, in this case there are 1, 2, 3, 4 blocks, on that set of blocks you put an F structure. So maybe I'll draw this set of blocks. You put an F structure on this set of blocks, and that is an F circle G structure. Sometimes an F circle G structure is called an F assembly of G structures. Okay, so what we've seen here is that an endofunction structure on a set U is an S assembly of rooted tree structures. An endofunction is an S assembly, that means a permutation of rooted tree structures. S circle A. What we've done is we've taken the whole set U, partitioned it into pieces. On each piece we have put the structure of a rooted tree, and then on the set of rooted trees we have put the structure of a permutation. And this picture here is visual proof that end is S circle A. What can we say about the generating series associated to a substitution of species? So the theorem is that if F and G are species of structures, and we have to have this hypothesis that G of the empty set is empty. This is certainly true of rooted trees, because you need at least one element in a rooted tree in order to have a root. Then we have, for cycle index generating series, Z of F circle G of x1, x2. It's a bit complicated. It's Z of F, and now you substitute in place of x1 ZG of x1, x2, and in place of x2 you substitute ZG x2, x4, x6 and so on, and in place of x3 you substitute ZG x3, x6, x9 and so on. This is certainly more complicated than what we saw for sums and products, and in fact the proof is harder, and I'm not going to prove it in this course, though we will play with these formulas. For the type generating series, we have f tilde g of x. So this is obtained by substituting in place of x subscript I, x to the power I. So you can just see that this immediately becomes g tilde of x comma g tilde of x squared, g tilde of x cubed, and so on. The simplest is when you take f circle g, just the exponential generating function, then it turns out to be f of g of x, just the composition of exponential generating functions. And of course, as I explained, A implies B and C, but A is not so easy to prove. This operation here, taking series f and a series g and getting this f circle, this complicated thing here, it's an example of what is called Plastism. So let me define Plastism first. So given formal power series f x1 x2 and g x1 x2 formal power series, and you need the assumption that in infinitely many variables. If you look at last week's practice assignments, I have given you some more details about how we should think about these formal power series. And you assume that G has trivial constant term. Constant term is 0. That means the coefficient of 1 is 0. The plastic substitution of G into X. Is defined as f circle g of x1 x2 is equal to f of g. So in place of x1 you put g of x1 x2, in place of x2 you put g of x2 x4, and so on. And so what this theorem above is saying is that ZF circle G is ZF circle CG. Let's just look at a couple of simple examples of plastic substitution. So what is G circle XK? Well, G circle XK means that you just take G and in place of x1 you put xk, in place of x2 you put x2k, because you have to double the index of the variables, x3k, and so on. And what is xk circle G? Well, here again there's only one variable, and that you have to, in place of that variable you have to substitute G, xk, x2k, x3k. So what we have is that G circle xk is equal to xk circle G. And another special case of this is that xk circle xl is x of k times l, which is the same as xl circle xk. This plastic substitution takes a little getting used to, and in fact it is not a very simple operation, but certainly this part C here is something that makes life very interesting. So let's just look at a simple example here where we can actually do some computations. So this species of endofunctions, right? How many functions are there from n to n? Well, it's just n to the power n. So what we have is that end x is sum n goes from 0 to infinity n to the power n x to the power n by n factorial, and this is S circle A of x, but S of x is just 1 over 1 minus x, so this is 1 over 1 minus ax, and so what you can say is that ax is equal to 1 minus summation n greater than or equal to 0 inverse. You can actually use this to try to compute the number of rooted trees with a given number of nodes. Let's look at the type generating series n tilde x. This is S circle A tilde x, which is zs of A tilde x, A tilde x squared, and so on, which is product n greater than or equal to 1, 1 over 1 minus A tilde x to the power n. And well, for cycle index generating series, what can we say? It's just going to be the product n goes from 1 over 1 minus, I'll just leave it at xk circle A tilde. Let's look at a couple of other interesting examples. This one is very beautiful and simple. The species of partitions. Par is E circle E plus. What is a partition? Well, you have a set U and you have to divide it into blocks. The only condition being that the blocks, each block has to be non-empty. And so here's an example of a partition. But this is the same as dividing the whole set into non-empty subsets, and just which is what E circle E plus does. So if you want, you can view this as an E plus structure is just a non-empty set. So here's one non-empty set. Here's another non-empty set. So these are all E plus structures. I think it's lowercase plus. And subscript plus. And on the whole thing, you put an E structure. So straight away, we can get something about the generating function, par x. So this we know is the exponential generating function for Bell numbers. The number of partitions of set partitions of n is given by the nth Bell number, and this is going to be exp of, well, E plus is exp x minus 1. Just fall straight out of this description of par as E circle E plus. Par tilde x is exp of E plus tilde x plus E plus tilde x squared by 2, and so on, which we can think of as exp of, so E plus tilde x is x plus x squared by 2 plus, no sorry, it's just x plus x squared plus e tilde, right? And then this second term will give us x squared plus x to the power 4 plus x to the power 6, all this divided by 2. And then the next term will give us x cubed plus x power 6 plus all this divided by 3. And just rearranging these terms, we get x of x plus x squared by 2 plus x cubed by 3 plus, and then x squared plus x to the power 4 by 2 plus x to the power 6 by 3, and then x cubed plus x to the power 6 by 2 plus x to the power 9 by 3, and so on, which is just x of log of 1 over 1 minus x plus log of 1 over 1 minus x squared plus log of 1 over 1 minus x cubed, and so on, which is nothing but product k greater than or equal to 1 over 1 minus xk. This is the generating function for integer partitions. And that should come as no surprise. Two set partitions are isomorphic if and only if they have the same shape, and the shape of a set partition is an integer partition of the size of the set. Now we can also look at another example. So if the set partition example corresponds to Stirling numbers of the second kind, this one corresponds to Stirling numbers of the first kind. A permutation is an assembly of cycles. C is the species of cycle structures, and visually this is of course very simple. Any permutation has a cycle decomposition, maybe some 2 cycles, maybe a 4 cycle, and so on. And you can just take each cycle as a block. So this is S, this is E circle C. And you can again write down the generating series is 1 over 1 minus x, which is the x of the generating series of C. So we know the generating series of S, and so again from this we can get the generating series of C. Just log of 1 over 1 minus x, something which you can calculate by other means as well. S tilde x is, well, we know this, it's product of 1 over 1 minus x to the power k, k greater than or equal to 1, and that's going to be x of summation k greater than or equal to 1 C tilde x to the power k by k. But recall that, you know, if you have 2 cycles on a given set, they're always isomorphic, and so the type generating function for C is something we actually know. It's just x over 1 minus x. And so what we get is this rather remarkable identity that product k greater than or equal to 1 over 1 minus x to the power k is x of summation k greater than or equal to 1 over k x to the power k 1 minus x to the power k. And for cycle index generating series, well, we know that the cycle index generating series for S is product let's say k greater than or equal to 1 over 1 minus xk. But on the other hand, that S is E circle C tells us that this is equal to exponential sum k greater than or equal to 1 over k z c xk x2k and so on. You'll see on the practice problems that it's actually possible to use this to solve for ZC and recover the cycle index generating function for cycles.